What is infinity? Hi, my name's Philip Brown. I'm the Bearded Math Man. In this video, I'd like to talk about the idea of infinity, and what we're going to do to explore that is we're going to learn a little bit about, you guessed it, prime numbers. So first of all, infinity is not a number, it's an idea. Nothing can ever equal infinity. I mean, you ask kids a lot of the time, what's the biggest natural number? A lot of the time they say infinity. No, not a number. And I'm going to show you that in this video right here. And we're also going to call into question if infinity is even real. Pretty interesting stuff. So let's get started. Now it's pretty easy to understand that natural numbers, the counting numbers, 1, 2, 3, 4, and whatever, it's pretty easy to understand that those go on forever, which is the idea of infinity. They just keep going forever and ever and ever. So to kind of explore that, let's consider how many prime numbers there are. See, back in the day, Euclid said, look, there are two possible answers as to how many primes there are. There are either infinitely many or they're finite. So he did this thing called a proof by contradiction. He said, well, look, I believe there are infinitely many primes. So what if we assume that that's not true? What if we assume there are finite primes and explore that and see if we can find a contradiction? Let's see if we can prove that it's false, that there are finitely many primes. In other words, they're countable, like you could collect them all. Now we of course know that there are a lot more than this, many primes, right? But let's say that was it. And it doesn't matter. This argument, you could list as many as you want and you could do the same argument and it will still work. So if that's the number of primes that exist and there are no more primes, that's it. If we take their product, like that, and then add 1, that number will be prime. Because here's the collection of all the prime numbers right there. None of those numbers is a factor of this. Therefore, this has 2 factors, which is the definition of a prime number. Therefore, we have proven that it's impossible to have a finite set of prime numbers, so it must be infinite, because that's the only other possibility. Case closed, right? Or is it? We have a lot of trouble with really big numbers and collections of really big things. Even in our language, we have some things that, well, we only have the plural word for them. For example, sand, hair, rice, shrimp and fish. One that's really weird is moose, because all the others are so abundant and frequent. We don't distinguish between one of them in the entire collection. Like you have a grain of rice, we don't have a word for just a grain of rice. We have to use the phrase grain of rice. Big numbers of things really baffle us. We don't really know how they work. We don't even have the language to, well, address them. We just put them all together. Now, here's the thing though. There's a lot of sand, but it's finite. We could collect it all. We could collect it all and we know how much there would be. It's finite. It's not infinite. And what about stars? Well, we have the thing, we call it the observable universe. It's how far we can see. We really don't know what's past that. We can imagine maybe it does go on forever, but maybe it's bounded, maybe it's collected. And maybe there's a bunch of other ones too. We don't know. It's a big guess. Same with infinity. So back to the primes. There's a whole bunch of study going on to try to find the next big prime number or patterns in prime numbers. So consider this string of prime numbers. So one of the ways that patterns of primes is being explored is looking at the difference between consecutive primes. The difference between 2 and 3 is 1, but that's it. That's the lowest. The next lowest is, of course, 2. But they're always even. But 2. If you have a pair of primes that are separated by 2, they're called twin primes. You see? Those are twin primes. Those are twin primes. But as of now, we have not yet been able to find a pattern that can predict these gaps. And then that way we can find the next prime. In fact, we don't even find the next prime numbers very often. There's a project called Gimps, Gimps, where you could actually sign up and at the nighttime or whatever, you could have your computer help search for the next big prime number. They're called Mersenne primes, but whatever. I mean, if your computer finds one, you get a little bit of cash and a little bit of fame. But why all the fuss? What's the big deal, right? I mean, prime numbers, who cares? Well, it turns out, when you go shopping online, your credit card information is encrypted. And the way it's encrypted, roughly speaking, is they take 2 really gigantic prime numbers, multiply them together, and that number is given to the merchant, and the merchant uses that number to encrypt your credit card information, and it's sent over the internet, and then the financial institution or whoever receives it, they have the two gigantic numbers, the two key numbers, and from that they can unlock it and get your credit card information and whatnot. That's how it works. And you might be thinking, well, geez, a 2-number code? How can a 2-number code be secure?
Tell. I knew it would work. All right, give it to me. The combination is 1. 1. 1. 2. 2. 2. 3. 3. 3. 4. 4. 4. 5. 5. 5. So the combination is 1, 2, 3, 4, 5. That's the stupidest combination I ever heard in my life. That's the kind of thing an idiot would have on his luggage.
Thank you, Your Highness.
What's the combination?
1, 2, 3, 4, 5.
1, 2, 3, 4, 5.
Yes.
That's amazing. I've got the same combination on my luggage.
Well, here's the thing. The last number found by the Gimps project was in 2013, and it was so big, it was almost, like if you print out the text file of it, it's almost 8 megabytes. To put that in context, that's the equivalent of almost 2 pop songs recorded as MP3s with high quality. That's a huge, huge, huge number. These numbers are massive. For that matter, it takes these massive computers, these supercomputers with like 32 cores, working for days and days and days, doing nothing but verifying if these numbers themselves are prime or not. So the 2 giant numbers, that's enough because they're so huge. But they're not infinite, they're numbers. We could just square them and get a bigger number. It's crazy. Now, back to the prime thing with this right here. Here's the thing I'm going to try to show you. There's infinitely many primes, but the gaps get infinitely large. We can have infinitely large numbers within an infinite set. That just blows my mind. Do you remember factorials from back in the day? You know, that's like 5 times 4 times 3 times 2, really times 1, but you don't really need to write the 1 because like that. Remember those? Yeah, well, check this out. 5 factorial, it equals 120. 5 factorial plus 5 is composite. 5 goes into it because 5 goes into this number. It's 120, right? Because the way we got that number is 5 times 4 times 3 times 2, right? You add 5 more, well, that's kind of like skip counting, remember? Like 5 times 5 is 25 because 5, 10, 15, 20, 25, right? Remember how all that works? So this is like skip counting one of the factors of the original number. So it's composite. Now, of course, it's composite. It ends in 5, but it always works for any number like this. Watch. That's divisible by 4 because 4 is part of this number by multiplication. We add another 4. It's kind of like skip counting again, right? So it's composite. Now, you might be thinking with the 4, of course, it ends in 4, but things that end in 3 are sometimes prime, right? But this one won't be because 3 goes into 120. It was part of the number, right? We add 3 more again, and same with the 2. So what that means is starting at 121, we have a gap of 4 numbers that will be composite. Big deal, right? Well, thing is, factorials get huge really fast. We could do the same thing with 100. Now, 100 factorial is way too big for me to write. I'll run out of chalk. 100 factorial plus everything all the way down to 2. You guessed it. It's going to be composite for that same reason. Those are all composite. This number right here, we can do this forever. We could do this for 100 trillion if we want. And then we'd have a gap of, well, 100 trillion, well, just minus 1 because the plus 1 gets things kind of screwy, but that's arbitrarily large. That's a massive number. We could do it with Googleplex. We could do it with any number you can think of. Since the natural numbers, like 100, are infinite, we could get an infinitely large string of numbers between consecutive primes. Let me show you one more thing. Let's make this general, okay? So a and x are natural numbers greater than 1, and a is less than or equal to x. Then consider x factorial. Add a to it, composite. Yep. A could be anything from 2 all the way up to x, and x could be any number you can think of. I don't even know if that's not approaching infinity, I don't know what is. And then you could square that. You could actually make this number to the power of itself and do it again. And there will be a gap that large, all of those digits large, between consecutive primes. But yet, the primes are infinite. There's infinitely many primes, but the gaps get infinitely large. We can have infinitely large numbers within an infinite set. That just blows my mind. Now let's muddy the waters just a bit further, shall we? Check this out. There's this thing called the twin prime conjecture. And I told you about twin primes just a moment ago. But the conjecture is that there are infinitely many twin prime numbers. So that means that you could have that big giant gap that we just had, and then all of a sudden, boop, we'd have two primes right next to each other, just separated by 2. That's the conjecture. Now, it's not an axiom. It's not as strong as an axiom. It's a conjecture because we're not really sure, and we think we can prove it. Turns out we're really, really close. A couple years ago, out of nowhere, somebody proved that there was going to be a gap of no more than 70,000 between primes. We could consider those consecutive primes. And then it got better, and it got better, and there's like nerd fight on the internet, which was fascinating and fantastic. I like watching nerds fight. But anyway, the gap supposedly might be as low as 16. Crazy. Now that would mean that we'd have like some giant number. Let's say ABCD is just some weird number and it's prime. And then there would be another number just 16 digits away that would also be prime. Now if you're talking about numbers that are like thousands upon thousands upon thousands of digits long, millions of digits long even, 16 is nothing. That's just the smallest of gaps. So it's weird. We're going to have this vast space of desert, no primes, and then poof, a cluster. Kind of weird. Now, while it's a conjecture that twin primes are infinite, there's infinitely many pairs of twin primes, we have found 2 gigantic twin primes. They are separated by just 2 digits. They're right here. Now, you might think that's one of them, but it's not. Hold on. That is a really huge number. But look, it's not prime. It ends in 5 because we're not done. In fact, I'm running out of room, so I got to do a little bit of exponent writing here. So this is going to be that number times 2 to the power of. Now some of you might recognize that we're building it's called a Mersenne prime, which is. Now if we had 2 numbers that are prime and they were twin primes, one would be 2 to the power of p minus 1 and the other would be, okay, see how this works is p is a prime number. So let's start with the first prime, 2. 2 squared is 4. 4 minus 1 is 3. 4 plus 1 is 5. Those are both primes. They would be twin primes. They'd fall in line with this right here. Now, not all twin primes, I don't think, are Mersenne primes. This is a specific style of writing a prime number and finding a prime number named after the mathematician Mersenne. But anyway, this right here is not the prime number. Holy moly, that's a big number. Now the next twin prime is, see that? So there's the other. This is the pair. This number plus 2 is this number. They're both primes. They're twin primes. Those are the largest pairs of prime numbers that we have been able to find. Now again, these prime numbers, they are like 57 million digits long and longer. Oh, it's just nuts. And the thing is, we can't even really get our minds around a number having that many digits, much less what that many digits really means. If you try to think of something, a physical quantity like that, oh man, just doesn't work. We can't get our head around it. Man, it's completely an abstraction. So maybe infinity isn't real. So all of this stuff about, well, infinitely many primes and sets of infinite things, it's all beautiful and wonderful and good as long as you believe infinity is real. But if you don't, then it all falls apart. You see, the thing you believe is true is only as strong as your supporting belief. It's called a presupposition. So in order for us to believe that there are infinitely many primes, we have to believe that there is such a thing as infinity. The point of this entire thing was, well, number one, to do some kind of cool math and explore some properties of prime numbers and maybe create some interest, but also to show that, well, math is contentious. It's not this rock solid thing. It's plastic. It's changing. People are arguing about it, and it's dynamic. It's kind of interesting and cool. It's lively. My point is not to convince you that infinity is not real or that infinity is real. The point was just to get you to think. My idea is that if I can excite your thinking about math, then might create some interest and might make math a little easier for you, because I believe people learn what they want to learn. Yep, they do. People also learn together, and people, students like you, don't need people like me to be an expert for you. I'm more your guide. Like, I didn't teach you how to do anything here, I just tried to introduce things. So, again, my name's Philip Brown, and I'm the Bearded Math Man, and if you don't know, I have a mission. I'm trying to change math from a hurdle that's in the way of young people's dreams and goals into a platform upon which they can achieve great success. I have a project and a mission. I am trying to create a body of materials that will help both students and their parents and teachers get kids all the way through high school in a way that promotes future success. I don't want you just to know the thing you're working on right now. I want you to know it in a way that you can use that knowledge in the future, and everything will be easier for you. You can check me out at my website, beardedmathman.com. You could really help me out if you like this video. Just leave me a comment, click like, maybe subscribe. And if you are fortunate enough to, well, be in a position to help with a project like this, you can visit my Patreon site. I'll put a link in the description below. Anyway, like it, hate it, whatever. I really do want to thank you for your time. I hope I stirred some curiosity with you. Anyway, have a good day.